is Dacen Waters. I'm a postdoc here at the University of Washington. I'm an experimental physicist, and I work on a set of quantum materials. I know everyone's eager to break out these 3D glasses, but I'm going to stick to 2 dimensions. I work on 2-dimensional materials, and I want to talk to you tonight about some of the cool things that we can do with these materials, stacking, twisting, and a bit of magic that's going to come along for the ride. Technical difficulties already, great. Okay, there we go. All right, so what do I mean by quantum material? We're going to be talking about quantum mechanics, the physics of the very small, right? So atoms, electrons, how they move and interact with one another, right? And then whenever I say materials, I mean something very specific. I mean a crystalline arrangement of these, a periodic arrangement of these atoms. Okay, so this is a crystal structure, and we're going to be talking about the electronic properties of these materials, how electrons move through these materials, and what properties they might have. All right? And whether or not you're aware of it, you're probably quite actually familiar with a quantum material. This is a picture of one of the first silicon transistors that was invented back in the 1950s. And it is a semiconductor. It's a quantum material where sometimes electricity can flow and sometimes it doesn't. That state of whether electrons flow or not in that material can be translated in binary, 1s and 0s. We can do operations with these. We can make them really small and cram a few billion of them into the processor on your phone. And you get all the marvels of the modern technological revolution that we're in, right? So next time you're scrolling TikTok on your phone, you can thank quantum mechanics for that. And I'll let you decide if that's a good or a bad thing. So that's where we've been with quantum materials. We can do a lot with them. They're very powerful. But I want to talk about where we're going next. And so my work focuses on what are the cool things that we can do with these materials, okay? And so I want to convey, you're going to learn a lot of cool physics tonight. You're going to see a lot of cool images. I want to convey 2 ideas. We're going to keep it really simple. The first idea, if you only take 2 things away from this talk, this is one of them, is that structure determines properties, okay? That's my first big idea. So let's walk through an example of what I mean by this. All right, so let's take diamond, a material that everyone's familiar with, right? Very, it's transparent, it's very tough, strongest material in the world. It's electrically insulating, and I want to compare that to the case of graphite, the stuff that's in your pencil lead. In some sense, I can't think of a more opposite material. It's opaque, it's very brittle, it's electrically conducting. Please don't go like putting your pencil up to a battery, just trust me, it's electrically conducting. You might ask, why am I comparing these 2 materials? They're so different. Well, they're made from the same atoms. They're made of carbon atoms, right? They're just arranged slightly differently. So this is the atomic structure of diamond. It's this like complicated looking cubic lattice. This is the atomic structure of graphite. It comes in these layered hexagonal sheets, right? And you can already see why graphite's a good writing utensil, right? The layers come off as you drag it across the page. So just taking these same atoms and rearranging them slightly differently gives you vastly different properties, right? That's what I mean by structure drives properties. Okay? Obviously, it means what is it made of, but also how is it arranged. And this is a particularly relevant example because some physicists back in 2004 looked at the structure of graphite and were like, oh, hey, like what if we could isolate this to just a few atoms thick? And they were actually able to go a step further and isolate it to a single atomic limit. And this is called graphene. It's the first ever 2-dimensional material. There was a Nobel Prize awarded for this. It's 2-dimensional in this sense that if I put an electron in here, it's confined to the plane of the graphene, right? There's only x and y. There's no z direction, right? You might be asking, like, what is this remarkable, like, scientific technique? This must be $1 million instrument to isolate a single layer of graphene. Some of you already know the butt of the joke. It's not. It's just Scotch tape. We just take some Scotch tape, we put graphite on a piece of tape, and you just cleave it a few times. You put it on a substrate, and you're bound to get some graphene, right? Here's a picture of what that kind of looks like. So a really accessible technique. And it's really cool. Graphene's a metal. It's a very special metal. It's interesting in its own right. But why I bring it up is that it really sparked a revolution because we realized we have all these different layered materials. And they have different properties. We can do semiconductors that are 2-dimensional. We can do insulators or magnets. Whatever you want, we have it as a 2-dimensional material. And owing to that 2-dimensional material, I can start taking them 1 layer at a time, 1 by 1, picking them up and stacking them together, like so, just a little schematic of this. And whenever I create this like final composite object, for this example, I don't care what the individual layers are, but the composite object is going to have vastly different properties than any of the single layers by themselves, right? Because we know that structure determines properties. So this is actually what I do in the lab all day. I get to play, we all often make the analogy that I'm playing with Legos. I'm just taking all these materials, I'm combining them in new and different ways to come up with some engineering application or some new physics that I want to see. Okay? So 2D materials are really cool. We can combine them in a lot of interesting ways, and we actually have a kind of a novel tuning knob. So here I'm showing 2 sheets of graphene, you know, my hexagonal graphene lattice. They're right on top of each other, so you can't distinguish them now, but I'm going to hold one of them fixed. I'm going to start rotating the other, and something quite remarkable happens. See if we can see it well in this lighting. Can we see this like larger scale periodic pattern emerging? Yeah, so this is called a moiré pattern. It depends on the, I don't know, you can look at it with the 3D glasses. This was not planned, I don't know. Oh gosh, now I want to. All right, anyways. So this moiré pattern, this interference pattern, it depends on the twist angle, right? That it grows and shrinks depending on the angle. If I freeze it here on 1, you can just see that like larger wavelength pattern. You know, you might think that this is some cute trick that I'm playing, right? It's some kind of optical illusion. But remember, in these materials, structure drives properties. Structure determines properties. So this is going to radically change what happens to the electrons in that system. Just to give you an idea what it looks like, this is an image of a flake of graphene that I exfoliated the other day. The color contrast shows like different numbers of layers. So like, does my laser want to work? 1 layer, 2 layer, 3 layers of graphene, right? There's a scale bar here, 20 micrometers, but just for reference, this is a microscope image to scale of a typical human hair. So we're talking very small, but we can reliably pick these up, stack them together, and fashion little devices out of them. So these gold wires are like leads, and I can start poking and prodding this material to see what cool stuff happens to it. Okay? So to talk about what cool stuff can happen, I want to introduce my second point, right? So this is the second idea. If you only remember 2 things, so this is the second one. When electrons start to interact, cool things start happening, all right? So what do I mean by that? Well, there's lots of ways this can come to play, but let's just imagine I have a, this is a cartoon picture of my crystal lattice here, and I ask what happens when an electron goes into the system. If I try and pass a current through this, and this is just some normal material, the electron's going to go through and it's going to bounce off of all these ions in the crystal lattice, and it's going to give off waste energy in the form of heat and light. That might be great. You might want a light bulb, you might want a heater, but if you're trying to do low power electronic devices, or if you're trying to transmit a bunch of energy over long distances, this waste energy can be problematic, right? So one cool thing you can do is you can realize that this picture, I'm only considering 1 electron, and I can accurately describe the physics as it bounces off these atoms, just considering that single electron. It doesn't care about all the other electrons that are around it. We'll often call this a single particle picture, the single electron picture of this material. But if you start letting the electrons interact with one another, some really interesting things can start happening. So, you know, you have your single electron, it's been sitting on the couch. Maybe it's been a long pandemic, you know? It's watched way too much Netflix. What are any of us in that situation going to do, right? We can turn to online dating, right? So this electron can go on to its favorite. I'll be here all week, yeah. This electron can go into its favorite dating app of choice, Spender or CUWiP. Okay, that's it. I'm done. All right, so it can go into its favorite online dating app, and it's like, okay, it needs to make a profile, right? So it's a spin-up electron. It's moving to the left. It's got some momentum left. It needs to find an appropriate match. And for this example, you know, it finds an electron that's spin down, momentum to the right. And if the conditions are just right, it can pair up. Okay, so these electrons start interacting. They start pairing up. There are other ways to pair up, if you know what I mean, but this is good enough for now. This is called a Cooper pair. And a Cooper pair does something quite remarkable. When it passes through a material, it does so with absolutely no energy loss. No energy loss whatsoever. When I mean no energy, I mean none. It's perfect. Nothing's ever perfect in physics. So superconductors, which is what this is called, superconductivity, they're quite cool. They're one of the more exotic phases of matter that we can create in the lab. You might know where I'm going with this. So we have these electrons in graphene. Ordinarily, single particle picture is good enough. Then we start using this tuning knob of twist angle, and when we approach something called the magic angle, it's about 1.1 degrees, these electrons start pairing up, and graphene becomes a superconductor. Okay, so let's not get lost where we started. We started with just pencil lead, right? And we use these key ideas that structure determines properties, and that electrons interacting, we can get some cool things happening, and we create superconductors. Okay? So with that, I'm going to wrap up. Remember my two big ideas? Structure determines properties. With 2D materials, we can combine all of these different materials in new and interesting ways. And when electrons start interacting, cool things start happening. And we're only just scratching the surface of what 2D materials can do. So with that, thanks for your attention.